Hey, thanks for that introduction, Wilma. And thanks to all of you for being on this call this morning, where I'm going to talk to you about factors affecting micronutrient availability with a focus on iron and zinc. And again, my name is Dr. Jim Ippolito. I'm an associate professor of soil fertility and soil health within the Department of Soil and Crop Sciences at Colorado State University. And so if you were to see an iron and or zinc deficiency in your plants, this is typically what you would see, and I'm just going to hit you over the head with it right up front. So iron deficiencies or intraveinal chlorosis, as you see in the left-hand picture, and zinc deficiencies typically, at least in corn, manifest themselves as this sort of muddled yellowish, light greenish band within the newer leaves. And both of these, to be honest with you, are typically found in newer leaves. We'll talk about this in a little more detail as we move along throughout this talk. So this figure here shows you all the micronutrients that are necessary for plant growth. There's 8 of them, right? And although these micronutrients are needed in small quantities within the plant, they can easily just be as limiting to plant growth as the macronutrients. So if we focused on iron and zinc, for example, right? So iron and zinc are highlighted here with these 2 red circles. And if you look at the very last column, the average concentration of iron and zinc within plants is 100 or 20 parts per million respectively. And those concentrations may seem low. And in fact, if we related those to the 4 macronutrients that I have listed in the top right-hand corner, carbon, oxygen, hydrogen, and nitrogen, these elements, iron and zinc, are extremely low, but at those concentrations, they are highly important for plant growth. And without available iron or zinc within the soil at adequate concentrations, we're going to see deficiencies like I showed you on the previous slide. Now, I want to put these concentrations within the plants into perspective based on those 4 percentages in the top right-hand corner. 45% carbon, 45% oxygen, 6% hydrogen, and 2% nitrogen on average are found within plants. Those are a percent, not part per million. If you were to convert those values to parts per million, plants contain 450,000 parts per million of carbon and oxygen, 60,000 parts per million hydrogen, and 20,000 parts per million nitrogen. Compare those values to iron and zinc, and you can fully understand the difference between macronutrients and micronutrients. Regardless if they are lacking in the atmosphere or the soil, you're going to see a deficiency symptom. And so with that said, we're going to focus in this talk on iron and zinc. And why are we focusing on iron and zinc? Well, I can tell you that out of these 8 micronutrients, the only 2 micronutrients that have ever been reported as a deficiency symptom in Colorado are iron and zinc. And so thus the importance of this presentation. So how do iron and zinc become available in soils? And to answer that question, we need to understand how iron and zinc cycle within soils themselves. And so there's 3 or 4, actually there's 4 major pools by which iron and zinc cycle within soils. So the pool in the center is the plant available pool. This is the pool by which plants derive iron and zinc. The concentrations of iron and zinc in the plant available phase are relatively small or low, and that's a disadvantage to plants. But where is iron and zinc found? It's found in the other 3 phases. Let's start on the left-hand side. So there's quite a bit of iron and zinc found in organic matter or organic phases. Those phases are degraded by microorganisms. Microorganisms use the carbon found in organic matter or organic phases as energy sources. And when they utilize that carbon, they respire CO2 and they release micronutrients such as iron and zinc. And they're released into the plant available or soil solution phase. That process can go on reverse, if the organic carbon present does not have enough iron or zinc present in it, where do these microorganisms get iron and zinc? Because they need iron and zinc just like plants, just like animals, just like humans. If there is not enough iron or zinc to maintain their body tissue, they scavenge it from the plant available phase. That's called immobilization. The other pool where iron and zinc reside is on the right-hand side. This is iron and zinc on adsorbed and exchangeable phases, such as the outside of clay minerals, or what you might know as cation exchange capacity. And iron and zinc can either adsorb or be desorbed from those phases. And it's simply a function of what other elements or ions are in the soil solution phase that can replace iron or zinc on the exchangeable phases. And the last phase, in the bottom center, by which iron and zinc are held are in solid mineral phases. And we see this all too often in our at least subsoils in eastern Colorado. Subsoils tend to have a high pH, and minerals such as iron oxides or hydroxides or carbonate phases, where zinc oxides, hydroxides, or carbonate phases simply precipitate out of the soil solution or the plant available phase. Now, some of this in the mineral phase does dissolve, but it can readily be reprecipitated. And if the plant can't see it because these reactions are occurring rather quickly, then the plant suffers. And the last thing I want to point out is that this, well, two points. That this cycle is relatively simple. Anytime you only see several arrows moving in a couple different directions, the cycle is simple. And iron and zinc cycling in soils is simple, although trying to wrap your head around what's going on at any given time is rather complex. But if you could recall, say, the nitrogen cycle where arrows are going everywhere, arrows are hardly going anywhere in this cycle. And in fact, where are the losses? Where are the arrows that are moving out of the soil? What I show you here is that the dominant export or loss of iron and zinc from soils is typically through crop uptake and removal. Yeah, there's a little bit of leaching with possibly dissolved organic phases. There's likely some erosional losses. If you're good at controlling both, your major loss pathway is through plant uptake. So what affects this cycle? Well, the factors that affect all micronutrient availability, and in this case for this talk, iron and zinc availability, are fivefold. Soil pH greatly affects iron and zinc availability. Soil organic matter content greatly affects iron and zinc availability. I think we sort of touched on both of those on the last slide. Soil texture greatly affects iron and zinc availability. Think about coarse textured soils versus fine textured soils. And you probably can answer the question, which one has more or less iron or zinc availability? Soil water content, and if the soil is flooded for prolonged periods of time, something we call redox potential will occur. And that affects iron. Does not affect zinc availability, but it certainly affects iron availability. And then the last point, interaction with other nutrients, for example, phosphorus. And so what I want to do is I want to focus specifically on these 5 points within the next several slides to give you a little more detail as to how each one of these factors affects iron and zinc availability. So let's go. The first factor I want to talk to you about is soil pH. And I can tell you that the ion charge determines the availability as a function of pH. And it's shown in this graph. Right? So in the graph itself, hopefully you can see my mouse. On the x-axis is soil pH from acidic to alkaline or basic conditions. And on the y-axis is relative availability from low to high. Now, I should tell you that this y-axis is typically on something called a log scale. Okay, and that's important. And if you look at the figure, the two lines that I drew within this figure are drawn that way for a reason, because the charge of each individual ion is affected, or the availability is affected by that charge as a function of pH. So what do I mean by that? For every 1 unit pH increase on the x-axis, zinc availability for plants decreases a certain way. And we can describe that decrease as a function of log base 10 to the power of that charge of the ion. So 10 to the second. If you did the math, that's 100-fold. And what this figure is telling you, and what I'm telling you, is that for every 1 unit pH increase in the soil, zinc availability decreases 100-fold. The same concept holds true for iron. For every 1 unit pH increase in the soil, iron availability decreases 10 to the third power, or 1,000-fold. And that's why these lines are drawn in this fashion. And I'll tell you that the same thing holds true if you went backwards, right? So for every 1 unit pH decrease, zinc availability increases 100-fold, and iron availability increases 1,000-fold. The next factor I want to talk to you about is soil organic matter. And soil organic matter is certainly an important source of micronutrients, iron and zinc also. Of course, they're both micronutrients. And why are they important? Well, that's because organic compounds or materials contain, among other elements, iron and zinc. And so when organic materials are degraded, they release iron and zinc to the soil solution. And that process is called mineralization. If you think about it, and if you could get your hands on organic amendments, they are also a good source of micronutrients. So for example, I could tell you for a fact, based on the last 40 years, roughly 30 of which I was a part of and still am, land application of biosolids within the state of Colorado. Oh yeah, zinc availability from biosolids is a great source in terms of that amendment. And we see biofortification or increasing concentrations of zinc in winter wheat grain in eastern Colorado due to land application of that material. You would find the same thing if you were to land apply manures or likely composts. And then point number 2 is that some organic compounds, after organic matter is degraded into simpler compounds, those compounds can actually help chelate micronutrients. The term chelate is Greek for claw-like or crab-like. So in this case, you can see that this organic compound on the left-hand side, it might have a section of it that's sort of opened, all right? And that section, in this case, can chelate or complex copper. This complex on the right-hand side of the 2 arrows keeps copper in solution. And this form of complex copper can be carried from some part of the soil solution towards the root surface and release copper so the plant can take it up. The same concept holds true for complexation via chelation of both iron and zinc. It says, therefore, less adsorbed or exchangeable iron or zinc on cation exchange sites. And here's a kind of a terrible example, because this example doesn't show you iron or zinc on the exchange sites of this clay particle. But the concept is pretty simple. And you, hopefully all of you understand this concept in soils. The more clay content that you have, the greater cation exchange capacity you have. And so the greater buffering capacity you have against that change when plants are taking up nutrients that are being essentially stripped off of the exchange sites. And this includes iron and zinc as well. So the CEC is lower in coarse textured soil, so there's less buffering capacity against change in iron and zinc in solution, where the plants pull up iron and zinc or absorb iron and zinc. So throughout this talk, I'm going to throw a few questions at you. And what I'm going to do, just to make this simple, is I'll throw the questions out to you. They're thinking questions, but because we're on Zoom, I'll just answer the questions for you, okay? So let's just keep this simple. So the first question I have is, can you influence soil organic matter or clay content with production practices? And you should say, well, maybe and maybe not, right? So if you change your production practices in such a way to hopefully increase organic matter content over time, then you should say yes, right? So if you're going from a highly tilled environment to no-till, and if you're lucky enough to plant cover crops and start doing things that would improve soil health, including organic carbon content in your soils, then yes, you can improve soil organic matter. We know this. We already know this. Clay content, on the other hand, I don't know any other way to improve clay content in a soil unless you actually import clay and put it in your soil, and that's not cost effective. Another factor that affects iron and zinc availability in our soils is water content, which is related to redox conditions or oxidation reduction conditions. And this affects only iron, not zinc. And so I state here, oxidation state highly affects availability of iron, but does not affect zinc availability. And I'll tell you why here on this slide. Okay, so under oxidized conditions, letter A over here, these are well-drained soils. These are most of our arable soils, if not all of our arable soils in Colorado. And in our soils in Colorado that are well-drained, well-aerated, we typically, in fact, more often than not, we find iron 3 present. This is relatively less available than iron plus 2. When soils are waterlogged for prolonged periods of time, 7 to 10 days, roughly at a minimum, this iron 3 is converted to iron 2. And iron 2 is more available. In fact, depending on conditions, iron 2 plus can be 10,000 to almost 1,000,000 times greater fold in terms of availability over iron 3. But the kicker is, in the above two scenarios, where do you grow your crops? Right? You grow your crops over here. And I would assume that if you're growing crops over here, you're not doing a very good job of growing your crops, right? Most of our crops that we grow in Colorado don't like their feet being wet. So we're over here. And so that's an issue. So both of these forms can be taken up by plants, but we typically grow our plants in oxidized conditions. The kicker is that this process of oxidation reduction only affects iron and not zinc, because iron can be found in iron 3 plus or iron 2 plus. But zinc is only found in one state, and that's zinc 2 plus, and it's not affected by redox conditions, at least directly. And then the last factor that affects iron and zinc availability is the interaction with other nutrients. And I think this is really interesting. It may not be something that you should be really concerned about, maybe as compared to points A, B, and C. But I think it's interesting nonetheless, just so you understand how this works in soils and in plants. So, for example, copper, iron, manganese, and zinc may all compete with one another for uptake into plants. And why is that? Well, here we are, 2020, almost 2021, and scientists like myself still really haven't nailed down the mechanism or mechanisms by which these 4 micronutrients are taken up by plants. And it's generally considered that all 4 of these elements are taken up in the same fashion, using the same active transport mechanism that carries these 4 elements from outside the plant root to inside the plant root, right? So if all 4 of these elements are competing for one pathway to enter the plant root, there's a bottleneck there, depending on the concentrations of these 4 elements within the soil environment. Another really interesting fact about interaction with other nutrients deals with phosphorus, and phosphorus can form associations with zinc or iron and create insoluble mineral phases present in the soil. So if you make an oops and really over apply phosphorus, which I'm assuming all of you do not do, But you can force zinc and iron to become unavailable or below the level by which we consider deficient in soils simply by over applying or applying in excess phosphorus. The interesting fact is that this goes both ways, and I would assume all the producers on this call today would not over apply zinc or iron to the extent where you would tie up phosphorus in your soils. I can tell you though, in systems in Colorado, this does occur, but it's typically in areas that are affected by historic mining operations. So it's not in the eastern plains of Colorado. It's up near, like Leadville, Colorado, for example. There's soils in Leadville, Colorado that go backwards and reduce phosphorus availability. You don't have to worry about this in your systems in eastern Colorado. I hope not. I really hope not. So with all of that said, let's get into some specifics and let's talk about iron specifically. And so when you see iron deficiencies, they look like this, right? And so, Dave, you're the only person I can see on my screen, so I'm going to pick on you. What does this tell you about one of the functions of iron in plants?
Might have something to do with chlorophyll.
Yeah, exactly. Thank you. That was like a little softball lob to you, and you just cracked it out of the park, Dave. Chlorophyll. Iron plays a major role in chlorophyll synthesis. And so when you have a lack of iron, you typically see chlorosis. And in fact, the telltale sign is, and we're going to get into this in a few slides, but it's interveinal chlorosis, meaning the veins of the leaves themselves are dark green, and in between the veins, you have a light green or kind of a yellowish color. And under low iron availability in soils, the chlorophyll production is reduced, and this is a telltale symptom of iron deficiency. Sometimes people misconstrue this for manganese deficiencies, but I can tell you that there has never been well, as far as I know, there's never been a confirmed manganese deficiency symptom documented in Colorado. I may be wrong, but that's what I've read year and year and year. Another really interesting fact is that iron is a component of an enzyme called nitrogenase. And why is that important? Well, some of you on this call probably grow legumes in your cropping systems. And so iron is essential to those nitrogen converting bacteria called rhizobia in the root nodules that you see in this top right-hand picture. Okay, the root nodules on alfalfa or clover or vetches or whatever you're growing that's a leguminous crop. And I tell you this because this is a really interesting story, and if you don't know this, you should know this. So if you want to, first of all, if you're growing a leguminous crop, you want to know whether or not the nodules are doing a good job of fixing nitrogen. If you remove a plant root from the ground and look at the nodules, in fact, crack them open, if you see that characteristic reddish pinkish color, that means that the rhizobia are highly active. The really interesting part about that picture is that red color is due to iron. And in fact, the compound that you see that creates that red color is called methemoglobin. It's just like our blood. It's basically the same compound as hemoglobin that's flowing through all of our systems. And so when I teach this in my class, I sort of get really excited about this because what this tells us is that humans are basically giant walking blobs of microorganisms. We are. we are so much in common. We have so much in common with rhizobia species and other bacterial and fungi, well, mostly bacteria, that we're giant walking blobs of microorganisms. So there's a connection here with what we're talking about today and us personally. The forms of iron that are taken up in plants, we sort of talked about this. They're taken up in iron 2+ or iron 3+. Most of our arable crops take up iron 3+. Under waterlogged conditions, we talked about this, iron 2+ dominates, iron 3 dominates under our normal, well-drained, aerated soils. And so I think I already answered this question earlier, but which one has greater availability to plants? Iron 2 is probably 10,000 to almost 1 million times greater fold in terms of availability to plants. versus iron 3 plus. And unfortunately, we grow our plants here. And that's a prelude to a few slides from now, FYI. So how do you identify an iron deficiency in our symptoms? Intravenous chlorosis, classic way to classify an iron deficiency, but that's not it, right? And so if you've done this for part of your career, then you know probably where I'm going with this slide set. But if you haven't done this, I think this will be a good learning example for you, okay? So here's a picture of corn in the bottom right-hand corner. And you can see that the deficiency symptom of iron increases as you go from older to newer leaves. And so what that tells you is that when you see a deficiency symptom of iron, more often than not, you're first going to see the signs in older leaves. And that's really important, okay? Because if you're typically classifying deficiencies for macronutrients, almost all the macronutrients, not all of them, but almost all the macronutrients in terms of deficiency symptoms, you're going to see in older leaves, not younger leaves. So what this tells you is, and it's shown here in this picture of this grape plant, that the deficiency symptom is on the newer leaves. And that tells you that, not that this is that important, but it's important just to understand what iron does and how it moves and is translocated in plants. Iron is not very well translocated within plants. It's highly immobile in plants. And so that tells you that when you see a deficiency, it's going to be expressed on the newer leaves. And that's unlike nitrogen, for example. Nitrogen is highly mobile in plants. And so you typically see deficiencies on the older leaves. Here's a peach orchard on the western slope. You can see that there's deficiencies on the newer growth. And if you looked at it up close in person, the deficiencies on the newer growth, it's classic intravenous chlorosis. So the veins are dark green, and in between the veins, it's chlorotic. General rules of thumb, if you're interested, there's plants that are highly sensitive to iron deficiencies, mildly sensitive, and have relatively low sensitivity to iron deficiencies in soils. Most of the crops that we grow in Colorado fall within the low to mild sensitivity category, if you look at the list. Of course, there are some plants that we grow here in Colorado, grapes, for example, that fall in the highly sensitive category. Okay, this is just a general rule of thumb. And of course, these categories are all affected by those 5 factors that we just talked about previously.
Dr. Jim, this is
Yes.
Merle. How are you?
Good. How are you?
Good. On this slide, I just got a conundrum there. I see soybean as high sensitivity, and then I see it at low sensitivity. Is that like a pan in the morning and in the afternoon, or what's going on there?
I don't know who's talking. I only see MKVD.
Yeah, that would be me, your old buddy Merlin. There you go. How you doing, Doc?
Hey, good, Merlin. How you doing, man?
Good, but I am trying to pay attention, and I am confused. Why are they on both lists? Actually, they're all 3 now, I see.
I love that you asked that question, Merlin. I really do love that you asked that question, and I'm going to show you why in a few slides.
All right.
Yeah, so stay tuned.
Okay, but I'm going to hide.
Okay, well, I'll see you later. You know, it's almost like I paid Merlin to ask that question. I really appreciate that. That's great. So I'm going to come back to that because soybean is sort of unusual in that it falls in all 3 categories. And so this is the prelude to that question. So how do plants alter iron uptake from soils? And so there's 2 strategies. And under strategy 1, there's 2 sub-strategies, right? And so there's either biological regulation of the rhizosphere pH, that's 1, or regulation of the rhizosphere redox conditions, that's 2, okay? So if you can lower the pH, and we talked about this already, right? If you lower the pH, iron availability, iron 3 plus availability increases 1,000-fold for every 1 unit pH decrease. And then if you're a plant and you can alter the redox conditions around the rhizosphere, you can convert iron 3 to iron 2. And I already told you that the concentration or the availability will increase about 10,000 to maybe a million fold. And plants can do this. So that's one strategy with two subcomponents. The other strategy is for the plant to create natural chelates from within the plants themselves and pump those chelates, they're called phytosiderophores, pump them out into the rhizosphere and grab a hold of nutrients, iron and zinc, copper, etc. Okay. And so these next couple slides, I believe, pertain directly to Merlin's question. So strategy 1 occurs in dicots and non-grass monocots. Okay, so if you're growing alfalfa or soybean, in fact, soybean is probably illustrated here in this slide set. This relates to those types of plants. So there's two mechanisms in strategy 1. Either you lower the pH or you cause a redox condition alteration in the rhizosphere. So this is what plants do to overcome an iron deficiency. And plants are not stupid. They're pretty dang smart. So to overcome an iron deficiency, they'll likely cause hydrolysis of water, so splitting of water inside the plant cell. And that frees up hydrogen, which is pumped. So first of all, that part takes energy. Then that hydrogen is pumped across the plasma membrane, across the root membrane, out into the rhizosphere. And that lowers the pH and increases iron availability. That's one mechanism. The other mechanism is that the plants can create products that can cause reduction in the rhizosphere. So one of those products is called citrate. And the plant can create citrate within the plant root. That takes energy. It's pumped across the plasma membrane. That takes energy. It goes out into the soil rhizosphere, and it causes redox conditions and alters iron 3 plus. It converts iron 3 plus to iron 2 plus. Okay, so both of these would affect iron availability. In this case here, that's increasing iron 3 plus when you pump hydrogens out. In this case, with citrate, that increases iron 2 plus. When those become free in the rhizosphere, typically what happens is there's plenty of organic chelates that are naturally occurring in the soil, come along and grab a hold of one of these or both of them. And there's a gradient between out here in the soil and up against the root itself. Okay, up against the root itself, there's typically low iron concentrations. And out here, as you go out towards the bulk soil, the iron concentrations are greater. There's a gradient. And so this chelate acts as a carrier to carry either iron 2 or iron 3 to the root. This R means that chelate releases iron 2 or iron 3, and that iron 2 or iron 3 crosses the plant membrane, and then that chelate can move back out into the soil and find more iron 2 or 3. So the really interesting thing that I should pay Merlin for is, why is soybean found in mild, medium, and highly sensitive categories? And really interesting because soybean varieties differ in their ability to regulate what occurs around the rhizosphere. So here's a classic example. This was published almost 40 years ago. And there were two soybean varieties that, this is from Perry and Jolly, and I can't remember what year this was published from, but it was obviously before 1982. So the 1982 publication is from a book. And so these two soybean varieties differ in their ability to regulate soil pH, meaning the one that's efficient, the one on the left-hand side, can pump hydrogen ions across the plasma membrane and reduce pH in the rhizosphere as compared to the soybean variety on the right-hand side. And this is indicated by a change in this pH indicator called bromocresol purple, right? So when the pH is less than 6.8, it turns yellow. And when the pH is above 6.8, it's purple. And this is a great example of why there's plenty of different soybean varieties that do this to lesser or greater extents. And that answers your question, Merlin. The other strategy by which plants can alter their environment surrounding the root is strategy 2. And this pertains mostly to the crops that we grow here in Colorado, unless you're growing alfalfa, for example. And grasses like wheat and corn. Wheat and corn and other grass species perform a different or use a different mechanism to alter the iron chemistry in the rhizosphere, and they create natural chelates within the plant root that are pumped across the plasma membrane and go out into the soil and find iron, chelate it, and carry it back to the root. So I'm not going to go through the big fancy name, but it's called a phytosiderophore. It's a chelate that's naturally created within the plant root. It has to be pumped. So first of all, that takes energy. It has to be pumped across the plasma membrane. It goes out into the rhizosphere and finds any free iron that it can find and carries it back to the plant root. And then there's another pump that takes energy that carries that complex into the root, and then it's released back or released into the plant itself. And then this cycle continues. It's sort of a circle, all right? The interesting thing about strategy number 2 is that this, you can imagine this, right? So if you're a plant and you're not experiencing an iron deficiency, you wouldn't create phytosiderophores, right? You would think you wouldn't want to expend more energy than you really have to, and that's true. So this release can be induced typically by low nutrient concentrations or low iron availability. So there was a study that was done in published in 1990. And here's some of these grass species. When in the presence of adequate iron, they create hardly any of these phytosiderophores. When you remove iron and stress the plant, you can see the increase, the relative increase in the amount of phytosiderophores that are created, right? So here we are with barley and wheat, they're kings. And so, you know, sometimes you wonder, well, why don't I see an iron deficiency in wheat here in Colorado? Well, this is probably one of the reasons why you do not see or typically see an iron deficiency, because most of our wheat plants are highly efficient in strategy number 2. All right, so you're growing something and you see an iron deficiency, how do you overcome it? This is a no-brainer, duh, right? You're going to apply an iron fertilizer. So not every iron fertilizer application rate is exactly the same, and I'm sure many of you know this. We typically use metal salts, and the metal salt that we typically use is ferrous sulfate. So it's iron 2+, which is 10,000 to maybe a million-fold greater in terms of availability. The key with this is that if you apply this to most of our soils, not all of our soils, but the soils that we have that are highly calcareous, that iron 2+ is almost instantaneously or readily converted to iron 3+, and it's precipitated out of soil solution as a mineral phase. So it becomes unavailable to plants quickly. Strategies to get around that, if you're applying to the soil, and that's strategy B. So banding typically can improve effectiveness, but it's not a long-term fix, right? In fact, there's no long-term fix unless you can cause your soil to become less calcareous. And that does happen in our soils in Colorado, and Clayne Jones from Montana State is going to talk about this in the next Zoom call. Typically what we recommend is foliar application, right? So if you see you perceive an iron deficiency, foliar application is probably your best bet. Once you see the deficiency, you're past the point where you should have fixed it. So to fix it quickly, you apply foliar applications of ferrous sulfate, and typical recommendation is 1 to 2% ferrous sulfate, iron 2+ sulfate, in about, so you put about 20 to 30 gallons of water per acre of this solution. Unfortunately, it's a temporary fix. So, you know, a rough rule of thumb is you apply every 10 days. And that probably could be altered depending on your experience. If you're working in organic, this can be classified as an organic amendment because it's mined as ferrous sulfate. You can create, or you can purchase chelated iron. They're typically commercial, right? You can go to Home Depot or Lowe's or your co-op and you can buy these materials. They're expensive. They're typically used on high cash value crops. They can be foliar or soil applied, and they can be applied as a liquid with other liquid fertilizer applications. So it makes it a little convenient. I think the interesting thing is if you're going to buy a chelated iron source, in order of effectiveness, not all these have the same effectiveness. So iron EDDHA is more effective than DTPA, which is more effective than EDTA. Okay. FYI. You can also purchase likely organic chelates as well. If you look at recommendations for crops, the top portion tells you, you can ignore the bottom portion because I don't know if anybody's growing turf on this call. So if you're growing turf, look at that, but I'm going to focus on the top portion. This is kind of a general rule of thumb for most of our crops grown in Colorado. If you're above 5 part per million DTPA extractable iron, you likely don't have a problem with iron. Okay, and then you can see if you're less than 5 ppm. And that's a rough rule of thumb. I've seen other crops that, they use maybe 8 ppm or they use 10 ppm in other states. So it's a rough rule of thumb, but I'd always keep in mind 5 to 10 ppm is sort of the magic area where you need to be for DTPA extractable iron. Okay, let's see, let's switch gears and let's talk about zinc. So the forms and functions of zinc in plants, not that this matters that much, but zinc only is taken up by plants in zinc 2+, whereas iron can be taken up in 3+ or 2+. That's the only form that zinc is taken up, zinc 2+. What functions? I shared with you a few functions. This list is not complete. The list that I shared with you with iron wasn't complete as well. But zinc is important for creation of amino acids and protein synthesis within plants. Actually, I think more importantly for this talk, it's needed for growth hormones, specifically auxins. And one of those auxins is called indoacetic acid, right? Why do I tell you that? Well, that is important for diagnosing deficiencies, okay? So what I state here is reduced growth hormone production in zinc deficient plants causes the shortening of internodes and smaller than normal leaves. And so when you see zinc deficiencies, especially in corn, I'm going to show you a picture here in a second. When you see a zinc deficiency, there's 2 telltale signs, especially in corn. In corn, the internodes are shortened. All right, so that's sort of a classic zinc deficiency. The other classic zinc deficiency in corn is this, it's really strange, but it's a muddled, chlorotic, muddled green or yellow area. You might see some interveinal chlorosis like you see here, but when you see a big white or yellow strip in corn on newer leaves, that's zinc deficiency. There's no other micronutrient or macronutrient that looks like this, okay? If you saw a zinc deficiency in tomato, it would look like this, and I think you might have a tough time classifying this, but it's sort of muddled green, interveinal chlorosis, and the plants would be stunted. So if you could put both of those together, you might think that that's a zinc deficiency, okay? And the telltale sign is it's in newer leaves. So that tells you that zinc is highly immobile in plants. Okay, interveinal chlorosis typically in younger leaves. You have this muddy green or yellow in the sort of the leaf center on younger leaves. Shortened internodes is classic. Smaller leaves is classic. And you might see delayed maturity or fruit that just looks malformed. Here's a really great example. Obviously did not come from Colorado. I don't know where this came from. I can't read what that says, Potawatomi County. I'm assuming that sounds like New England states. Somebody applied excess phosphorus to this system, and it likely bound zinc and reduced zinc availability to this plant, to this crop, this corn crop. So plants are shortened, stunted. If you looked up close and personal, you would probably see this white band like you see in the right-hand picture. Okay, we've already talked about this. So this white band here, classic zinc deficiency. For comparison, there's an iron deficiency. I would hope that all of you on this call go, oh yeah, they don't look anything like one another, because they don't. we just talked about this. So where are zinc deficiencies observed? They're observed in younger leaves. And so that tells you that zinc is immobile. Well, it's relatively immobile in plants. So the same thing holds true with iron as well as zinc. They're both immobile in plants. And thus you see deficiency symptoms occurring on the newer leaves. And that's unlike nitrogen, which would occur on the older leaves. Okay, there's a range of sensitivity. Most of the crops we grow here are, well, corn is here and highly sensitive. That's not surprising. Corn's where's wheat? Here's wheat over here, mildly sensitive. And I'm going to show you some slides that makes me wonder if our wheat grown in Colorado should be over here in the highly sensitive category. And that'll come at the end. So stay tuned. So how do you influence zinc availability in our systems? Again, we apply zinc fertilizers in the form of, one of the forms would be manures or biosolids or other organic amendments. We typically have 0.01 to 0.05% zinc. That's 100 parts per million to 500 parts per million zinc. Our plants need about, what do we need? 1.5 ppm in a soil solution. Actually, I think we need to be above, it's above 1.5 from what I recall, okay? So manures, compost, biosolids, plenty of zinc. You can apply zinc sulfate. That's a common source. It can actually be certified organic because we can mine zinc as zinc sulfate. It typically has a pretty good residual value if you apply it to soil. It can last maybe 2 to 4, maybe 5 years before you have to reapply. I think normal application rates somewhere between 2 and 10 pounds per acre. Of course, if you banded it, you'll probably be more effective, just like phosphorus or iron. You can purchase zinc chelates. They can be foliar applied. They can be applied to soil. The kicker here is that in terms of application to soil, zinc is typically more effective when you apply it to soil than iron. Here's the test values for most of our sensitive crops. 1.5 parts per million DTPA extractable zinc is considered adequate. That's the number that's always stuck in the back of my head over time. So let me briefly talk to you about soil testing. And we just touched on this a little bit for iron and zinc. So for most iron and zinc, as well as other micronutrients in the soil, they're typically found in either precipitated mineral phases or organic matter complexes. So that ties directly back to that cycling slide that I showed you up front. I would say probably greater than 99% of the zinc and iron found in our soils are found in these two phases. It might even be greater than 99.5%. There's a very small amount on the exchange sites, and the amount that's in the soil solution is really, really small. I mean, it's probably, I can't take a guess, but it's probably less than 0.1 ppm. So this is what we do, right? And most of you know this that are on this call. When we want to determine how much iron or zinc is available for plants, we take a soil sample and we send it to a testing facility. And they typically, here in Colorado, use a chelate extraction, right? So the typical extraction here in Colorado is DTPA. That's a chelate extraction. And that chelate, this isn't DTPA, but it looks something like this. And I showed you this picture before. This chelate can grab a hold of nutrients that are either present on exchange sites or maybe on the edges of mineral phases that contain iron, zinc, manganese, copper, and chelate or complex those phases into a phase that looks like this. So when the DTPA extraction is performed at a testing facility and they measure the quantity of iron, zinc, manganese, and copper in your soils, they're measuring this complex phase. That's what they're measuring. So I already mentioned this, the typical chelate lab extraction in Colorado is DTPA. Some of you may have used the Melic 3 before, and Melic 3 actually contains EDTA in it, another chelate. They're both chelating solutions. The universal extractant that CSU uses is called ABDTPA, and some of you may have used this in your past. And this is sort of, this was an attempt by Dr. Parvis Sultanpour and others to create a multi-extractant for Colorado soils. This extractant uses ammonium bicarbonate to extract phosphorus. You can actually use it to extract potassium if you were interested in potassium. Most of us probably are not, but it can be used for potassium as well. And then the DTPA is used for chelating micronutrients. Most of you probably use the first chelating extraction. So lastly, in this slide presentation, why the big deal, right? Who cares, Jim? I mean, who cares about iron and zinc? Like, I never see an iron deficiency or I never see a zinc deficiency. I have a really interesting story to tell you about some work that we're doing at CSU that's in its infancy. We're in our second year, and I'm going to show you a little bit of first year data. And so the big deal is this. So this is all focused on wheat. Okay, this project that we're working on is focused on wheat. And so the concept is this: we all know in production agriculture that we've done a great job of increasing yields over time. So yields have increased over time due to breeding. We've done a great job of breeding. But what happens is, and this is not atypical. So this is the study that was published in 2015, showing increases in yield on the x-axis versus zinc concentration on the y-axis. And what you see is a downward trend in zinc concentration in these three different locations. And this is not uncommon in the crops that you're growing here in Colorado. I bet you if you went back and looked at the concentrations of zinc in your grain over time, you would see the same trend. And why is that? Well, I can tell you, if you don't know where zinc ends up in the grain, it ends up in the pericarp. So here, if my fist was a wheat grain, right? The pericarp is on the outside of the grain itself. It's just like the outer covering of the grain. When we mill, we remove that pericarp. But if you were to use whole grain, you retain a little bit of zinc, but the entirety of the grain is here, and this pericarp is just the skin. So if you go from a small kernel over time to a larger kernel or more kernels, you have more of those proteins that are within the kernel itself. But the pericarp, the size of the pericarp doesn't really change that much over time, and thus we see this decrease. You may not see a perceived zinc deficiency, but we can sometimes pick it up in our grain. And that muddled gray horizontal line is sort of the cutoff that many of us call, if you're above that line, you're sufficient in grain zinc. And if you're below that line, you're likely deficient in grain zinc. That's the cutoff line based on, among other organizations, the World Health Organization. Why is this important? I'll tell you why this is important for you as a producer if you're growing grain, for a wheat grain. Across the globe, there are 2 billion people estimated to have zinc deficiencies. And across the globe, about 40% of dietary intake comes from wheat. So there's a connection here, and a connection directly to you, the Colorado producer who's raising wheat. So this is the study we're working on currently, all right? So one of the things that we did when I came back to CSU about 4.5 years ago, I said to Jerry Johnson, many of you know Jerry, who runs the wheat variety testing program at CSU. So, what else can we do with the data that you collect? And so one of the things that we started focusing on, among others, is looking at zinc deficiency or potential zinc deficiency in our wheat grain that we grow in Colorado. So this is 1 year's worth of data. Jerry has 10 research locations. I can't remember why we only chose 6. Probably because we're doing this on a shoestring budget, to be honest with you, okay? So we chose these 6 different locations. This data is from after wheat harvest in 2019. These are the DTPA extractable zinc concentrations in the soil at these 6 different locations, all right? If this dashed line, I don't know if that represents sensitive crops. This other dashed line actually should be 1.5. That indicates mildly sensitive crops. All 6 of these locations have DTPA extractable concentrations that are lower than that are sufficient for growing wheat. which is interesting in and of itself. And so, okay, so am I going to see a deficiency in my wheat? I can tell you that the wheat that was grown at these 6 different locations, you never saw that muddled chlorotic line on the wheat itself. You couldn't see it. But if you were to look at, this is showing you zinc grain concentrations at each one of these 6 locations for the top, I would consider the top 3 varieties that we grow in the state currently. So Canvas, Langan, and Snowmass 2. And you keep in mind the cutoff based on a number of different entities, 25 parts per million zinc. At each one of these locations, each one of these 3 varieties were below that threshold. And so this is the start of a program at Colorado State to help you, the producer, overcome this potential issue with zinc in your system. And we're doing the same thing with nitrogen, and we're doing the same thing with iron. I'm just not going to show you that data today. Okay, whew. With that said, I hope I see Dave is still awake, so that's good. I thank you for your time, and we have a few minutes for questions, I think.
So Jim, your low zinc wheat. I'm presuming if our soil tests were up in the sufficient range above 0.5, that the grain zinc would come up too?
That's a great question. So my answer, based on some of the work we've been doing at other locations for the last, oh my gosh, 20 years, would be, yeah, you would see in this case, this picture here, you would see zinc grain concentrations increase. But based on experience over the last 20 years working at sites in Colorado, it would not come up above 25 ppm. So I think we need to have our zinc concentrations in our soils in probably like the 5 ppm range, extractable zinc, in order to get these concentrations in these plants up here. Now, that's not to say that you can't apply zinc foliar application and get these grain concentrations above 25. But if you want to do this from a soils perspective, it looks like about 5 ppm is where you need to be. So, and it's really interesting, Dave, because this data for fertilizer recommendations are based on varieties that we don't grow anymore, right? And they're based on the fact that, geez, 30 or 40 years ago here in Colorado, our average wheat yields were what, 25 to 30 bushel, and we're higher than that now. So
well,
this
I
is
just
due to
know
evolution.
History-wise, any of the ground we have that has corn in the rotation, which is probably getting zinc, those soil tests are coming up slowly. But ground that's historic wheat, fallow wheat, or maybe has some millet in the rotation is never getting zinc. A lot of those zinc levels are non-detectables. I mean, they're probably under 0.1. So I just wondered if you've played any of this game on maybe some of the irrigated wheat or some of these fields that have a lot better zinc tests to verify what those levels would be. Because 5 is, I won't say it's non-economic, but it'll be a great challenge to get people to get any soil test up to that range.
Yeah. So I have played with that. And so this is work that Ken Barber worked on. He started in 1982, and this is land application of biosolids. And so I'm drawing from almost 30 years of experience in that realm. And when we apply organic materials that contain zinc, we see that zinc concentration in the soil, the DTPA extractable zinc, creep up over time. And we can easily get above 25 ppm grain year after year based on those organic applications. And the issue with producers in Eastern Colorado is, I realize that some of you live way far away from organic materials. And so what do? It's a challenge.
Well, but I think what Dave's saying is that because Jerry also does irrigated wheat trials, that in the irrigated wheat trials, you could test the grain zinc in the irrigated trials because those soils would likely have higher zinc levels because of the rotation.
And I might add, I was going to follow that up as well, Kent. How you doing? It's Merlin.
Fine. I wore my CSU tie today just for
I
Jim.
saw that. Let's let it go. I'm gonna have one, and I'll probably put it in the closet and hang myself later. But I shouldn't even joke about that. But if Dr. Jim, if you take these levels in, to follow up on Dave and Kent's, are you going to see that number in the irrigated trials probably significantly higher? Because like Kent was saying, I don't know what happened in eastern Colorado when they open up the ground out here, but our zinc levels in our dry land are still so low, below between 0.2 and 0.8 or whatever the majority. And you get in the irrigated and you're talking in the 4 to 8 range, common 2 to 4 range. So I just wonder if you would see that difference, and are you going to get paid for it? Because we're trying to help humans.
Yeah, those are great points. So, there's reasons why I don't work in irrigated ag anymore. And I don't know if Jerry Johnson has any wheat in irrigated ag. All this work came from the dryland locations that we're working on currently. But, if you think about the nutrient cycle of iron and zinc, that graph I showed you up front in the talk, it's affected by, among other things, dissolution reactions, mineralization reactions, and the release of zinc or iron from organic phases and mineral phases into the soil solution pool. And so what causes that? Oh, yeah, Sally said they have 3. We didn't use any of the 3 irrigated trials. Anyway, the story is this. If you think about the cycle of iron and zinc in soils, the only way that iron and zinc can get into the soil solution is via water. And so if you're under irrigated conditions, that's going to cause greater mineral dissolution or greater degradation in terms of mineralization rates of organic minerals, pumping iron and zinc, especially in this case, zinc, into the soil solution. And you're going to see that reflected in your DTP extract. And I don't know about getting paid for this. It's not been really discussed, but that would be really interesting to think about down the road.
Well, when you're looking at grain qualities for cattle feed, let's just throw humans in the same pocket in a sense. It just would make sense to me if there's a positive nutritional value for the product, if we can identify that and somehow get that into the sale of the product. That's really what we're ultimately, like Dave always comes back to. It's all about economics. In the end, we have to have as much price for our products as possible for our producers. Thanks for the presentation, Dr. Jim.
Thanks, Merlin. Good seeing you again.
Thank you, Jim, for the